Okay, so hello everyone. We'll be doing lecture 10, recommender systems. Spotlight myself. Okay, great. Um, so some logistics. Assignment 3 is due next Wednesday. Uh, Project Checkpoint is due next Monday. So this is all coming up next week. And also pick a time slot for your team to discuss project proposal if you haven't yet. So those are some suggestions. I think most of the teams have discussed this, but there's a couple of teams who are yet to do it. So if you're one of those teams, please set up a time and then we can discuss the project proposal. And also, your checkpoints are coming up like next week, so it'll be good timing. I mean, it'll be important to do this ASAP. Okay. Right. So today we'll actually look at ranking and types of ranking problems and examples of ranking. And so it's a fascinating area. And we'll also look at some real world examples of ranking as well, especially in the context of recommendations. So ranking problems, traditionally it's been like page and so this page ranking and or search ranking. So this is like when you search in Google um, and then you get a ranking of results. So that's page or search ranking. And then recommendation ranking is like, so this is ranking to help fine tune recommendations. So it's like you already probably have a list of recommendations and then you want to rank them better before you serve it to the end user or customer. So that's recommendation ranking. And then you have like image, video, and you can also say content ranking. There's like other kinds of content that you kind of want to rank. So it's kind of connected to this, but doesn't have to be. So that's image, video, content ranking. So today we'll probably mostly focus on recommendation ranking. Next lecture we'll look at page/search ranking, and we'll see. So search ranking is a search and recommendations ranking. There's a lot of jobs in this field. There's a lot of work that's been done in this field, and search ranking is like very old. Like Google is based on search ranking, right? Google was primarily a search company, so YouTube and everything came later. Gmail, everything came later. But first, it was like search engine. So you type something and then you query and then you get a result. So the process of going from query to a result. This is search ranking, right? This is the primary purpose, and so this problem is pretty old. Search ranking is pretty old, and but recommendations ranking is more new, right? It's a more new ranking area and very relevant today. So like I said, let's say you want to prep for an interview and then you're looking at you query for ML interview questions and then you get some results. Or let's say you want to query for ML ops and then you get some more results. So you can see clearly there's like, it's even the search results are organized by some ads, and then there's like the first result, and then there's things that are useful that you may want to check out, and then there's a second and there's a third. So this is like the ranking part, right? So how did this come up here, and then second and then third? That's the ranking, page ranking or search ranking. So we'll look at this in the next lecture. And if you just I just did a LinkedIn search for search ranking, and then I found these jobs. So like if you see search relevance and ranking algorithms, yeah. So also the area IR, you might have seen this before. So search ranking is traditionally fell in this area of information retrieval. And so there it includes concepts like indexing, query understanding, retrieval, and ranking. So you also see things like, okay, so this is just looking at one of the jobs, but experience in deep learning, experience of training large-scale machine learning models for online search. So the new thing with even search ranking is the use of machine learning models. So this is new. So there was search ranking before, but now we have machine learning models for search, online search, recommendations, ad ranking, personalized. So this is, recommendations. We're getting to recommendations as well. And then this is one more. I think this is a different company. And then you look at search ranking, relevance, personalization. So like this is pretty very hot area in the industry. So it's learning to rank. So this is like, we'll discuss this in the next lecture. Deep learning approaches. Yeah. So we'll cover learning to rank in the next lecture. So anyway, just start off showing this. So the second area of ranking, which is more recent, is what we call recommendations ranking. And this is something I'll cover in today's lecture. So in recommendations ranking, the idea is that you might be dealing with millions of items to recommend, right? So millions to recommend from. And this becomes really cumbersome to pass through a neural network model, and you have like millions of things, and then you're going to pick between the millions, and that's going to be a lot of train time, but also inference time. So to make it easier, you can do more lightweight candidate generation. So this is typically a lightweight model that kind of takes these millions and then makes them into hundreds or thousands. So it can also be thousands. So you take these millions, filter them down to hundreds of thousands of models. So it's a lightweight machine learning or neural network model. So doesn't use too many features or the full set of features, but it's kind of, and maybe it's mostly using user features, but a little bit of item features as well. Maybe you're using, I mean, you obviously use item features, but maybe you don't use content information as much. But you provide that at this next stage. So there's the first stage. The second stage of ranking, you provide that context. And then this ranking is going to take these hundreds of thousands and make it into several, so maybe 20s or 30s. And this is what you end up showing as recommendations. So these are your final ranked recommendations. Does this make sense? Any questions or thoughts?
Yeah. So is the candidate generation, is that just like some, like, could, like before it was ML, could it have just been like a filter to filter out like the bad items that aren't
Absolutely.
relevant?
Absolutely. Like if
Okay.
you already had, let's say, you had a user, let's take Instagram. A user has watched or likes certain certain categories or types, or a user likes certain a different users images or videos. So then you take those images and videos of the other users that this user likes, and then just generate kind of go through all the candidates that are similar to these set of items, so either images or videos, and then that's going to be in millions. But then you kind of filter it out, maybe using cosine similarity, and you can get it down to thousands.
Gotcha.
So that's going to be the most efficient, the simplest thing you can probably do is you already have embeddings for items, and you're going to look at the user and look at what they like, and then based on what they like, you kind of compare that to And you can just it's like, here's an example. So here's a user and they like image 1, video 3, image 5. Let's say these are the 3. So they like this of, so this is, let's say, user 10, and they like this of user 99. So you don't have to have user embedding, but if you have image and video embeddings, we can use this to expand the search, like search across all images, search across all videos that are similar to this image or this video, and then generate 1,000,000 candidates, and then filter them down,
Hmm.
maybe using cosine similarity. So, I mean, it's also nice because let's say you want to stay current in terms of what the user likes. So just look at what they've been liking in the last 5 days or last week, and what they have been liking. And then that tells you what they're really interested in the past week. And then use that and the embeddings that you might have already learned for these images from a different context. Like maybe you ran autoencoders on images, or you did some other model, deep learning model, and you understood images and you have embeddings for them. Handy. Doesn't have to be part of this model, but you have pre-trained embeddings, just use them and then just generate candidates and then start filtering them out using cosine similarity or something. But that's not very sophisticated, but it still gives you, it can give you 1,000 candidates, of which maybe 100 are good, right? So idea is like, even though we're using a crude algorithm to filter them, perhaps these thousands have 100 good results, and then the ranking is going to capture those 100 and put them in the front, and then you're going to pick like 20 or 30 of them and show them as recommendations for the user. And the advantage of this is, if the items keep multiplying all the time, then it's going to be hard to keep track of any IDs of these items or images or videos. So it's easier to just have a separate system that generates an embedding for even a new item, and then gives it to you, and then you just use it. So this really works with scalability. This is a very generic template, but it's a very powerful template. Like going from, so this is going from simpler ML/filtering model to more complex or complete, let's say, neural network model. And then you can actually have layers. Some, as some of the examples that you'll see, they might have like 2 steps, 3 steps instead of 2 steps. So you have a simplest model, simpler model, and the full-blown model that can only probably work if you show like 100 candidates, and then it can actually compute scores for 100 candidates at runtime efficiently, but not for like millions. It would not scale. So you would use a very sophisticated algorithm or a more complete algorithm, but over a few candidates, and be very accurate. So that's the idea of going from a simpler to the more sophisticated. So how does this connect to what we have looked at so far, matrix factorization, autoencoders? Think of it as like we only had one of these, which is the ranking model. We didn't think about candidate generation or anything because we were not looking at scalability. So now we have to look at both scalability and a proper recommendation ranking model. Does that answer your question? Like,
Yes, it does.
okay. So let's look at some examples. So the first one I want to talk about is recommendations ranking at YouTube. Here's a reference. It's a nice paper from, I think, 2016. So worth taking a look. again, it has something similar to what we looked at as a generic template. So this, so here we're looking at YouTube videos. So there's a video corpus, millions of videos, and you want to do candidate generation from these millions, which could be like, you're filtering down these millions, or maybe you have some preset filters that takes millions and makes them into a million or a few 100,000, and then starts doing the filtering process already candidate generation, but then you apply something else and then get it down to hundreds. And if you look at what's the input here, user history and context is being used as an input for the YouTube ranking model, candidate generation model. So what has the user viewed in the past, and what's their context, and what channels have they liked, where have they spent enough time? And with YouTube, you can actually get data on which videos were watched completely by a user to get a more high quality implicit feedback, right? So high quality implicit. It's implicit because the users aren't telling you that they like the video, but because they watched it completely, it's a high quality implicit feedback. So let's say fully watched. All right. So, but if you look at the ranking stage, okay, in addition to the user context, there is also more video features and other candidate sources that's being added here. And we'll look at what these, some of these might look like. But there's more detailed information that gets passed in to support the ranking better. So that may not have been included in the candidate generation stage. But also you use a more sophisticated or state-of-the-art model for a ranking here. The other thing is, like, you might use neural network model for both candidate generation and ranking, but the goal might be a little bit different. The goal here is to just get maybe good candidates, but not the best ones. The goal here is to, you already probably have good ones here, so you want to rank them really well. So that changes how you would actually design these models, right? So the challenge is to build a YouTube scale recommender, and as referenced in this paper, one is scale, second is freshness, third is noise. So the scale is like really high. Like for example, the model that they trained in 2016 had 1 billion parameters and 100 million examples. So these are videos, million examples. Yeah, so sorry, this is not videos, this is user video watch, right? So this is already a lot of parameters and examples, and this is in 2016. So it's anyone's guess on what the updated model looks like and how many parameters they actually have in their updated model. So scale is a big factor. And we know YouTube recommendations are pretty good. They're very, they have variety, they have relevance, they have freshness. So it's more like you watch something recently, or it doesn't matter. I mean, even if you watch something before a month back, the recommendations that you're getting is a mixture of something from the past and something that's very recent. So really surfacing the content that's getting generated on a daily basis. So freshness is important, and YouTube is recommendation system is taking care of that, and noise. So there is noise in the implicit feedback. So if someone watched a video completely, it's very likely that they like the video or the content or the type of videos, but maybe not. So there is noise because maybe they watched all the way and then they said, oh yeah, I don't know if I'm interested to watch something like this again. It's rare, it's not very frequent, but it can happen. So, and that's the noise. So and there can be other kinds of noise that come up here. So okay, so these are some challenges. And so for scale, the candidate generation part is really a key, right? So let's look at the candidate generation that YouTube had used, at least as of 2016. So they modeled the problem as a multi-class classification. So which means you have, let's say, a user profile, and then you went through some layers. And here you're actually going to predict across, let's say, 1 million videos. So it's a very extreme multi-class, which means like you have an extreme number of videos to predict from. And it's multi-class, which means you pick one of the classes as the best one to recommend to the user. Maybe others are also getting scored, but it's like a probability that sums over all these videos, and the probability is equal to 1. Total probability is 1. So so you can still recommend multiple videos from this, but you are trying to pick the best possible video in this kind of a modeling approach. So that's a modeling approach, and the model itself, they use a neural network model that uses nonlinear. Yeah, so I was going to say it's kind of nonlinear matrix factorization. It's kind of like nonlinear matrix factorization based on user watch history data. So which videos have they watched? But they also have some content data as well on the videos. So we'll look at the precise architecture. A positive example is a fully watched video. So a full video watched by a user counts as a positive example or target. So if you didn't fully watch a video, then we'll discard it, we'll not use it. A negative example, as you've seen before in machine learning models, where we're dealing with implicit feedback. So there's no explicit feedback. There's no one saying this is positive, this is negative. But positive is easy because you can infer it implicitly. Someone has watched it completely. But negative, so they do random sampling and they kind of filter it as well. So they do some important sampling to make sure the negative samples don't have an obvious bias or don't have positive examples in them as well. So important sampling is done here. Okay. Inference time. So latency requirements for generating recommendations is in tens of milliseconds. Like, let's say you go to YouTube right now and you refresh the page. You want to see a different set of videos. Like maybe you want to see it really quickly. So the latency has to be really low. So what they do is once they have user and video embeddings, they kind of use approximate k-nearest neighbors to pick among the videos and kind of generate 100 candidates instead of like if you had 1 million videos, you kind of want to boil it down to 100, just use k-nearest neighbors. So k-nearest neighbors can use cosine similarity. It can use Euclidean distance. So the distance can be anything, but k-nearest approximate KNN is like there's like really efficient algorithms to get results really quickly for like millions or even billions of items that you're searching from. So yeah, basically you say, okay, I have a user, and then I have videos. So you have like 1 million videos, and then kind of do this matching and then pick KNN gives you like 100 top results. And this is good. This is actually approximate KNN. So approximate KNN means you don't get the best 100, but it's approximately, so it's in the ballpark, which is good. So we don't have to necessarily get the best possible ones. If we get good ones, that's good enough, because we also have ranking that's coming up right after. And obviously there's overfitting and stuff. So if there is overfitting and then you're looking at the best possible results, because of overfitting, they may not be the best. So you might as well approximate without losing much. So approximate KNN is faster than exact KNN. So for that reason, you can basically use them and be efficient and get the top results, which can then go into ranking. Any questions on this? Questions or thoughts? So here's the architecture for candidate generation that YouTube uses. So you can see it has embedded video watches. So let's say there's like 10 videos that the user has watched, get an embedding for each of the videos and then average them. So I might have, like, user 1 might have watched 10 videos in the past week. User 20 might have watched like 100 videos. But once I get the embeddings, in one case I have 20 embeddings, in the other case I have 100 embeddings. But once I average, the dimensionality is going to be the same, right? It's going to be the dimensionality of the, so let's say this is 512 dimensional. So when I average, I'm still going to get a 512 dimensional vector, no matter how many videos you're looking at. So that's a nice thing about this. But if you're concatenating, the dimension would change. So you would be having, so that wouldn't fit with a regular neural network model. So then you have to pass it through an LSTM or something so that you can just replicate. It doesn't matter how many videos you have. But since you're averaging it, we don't have that problem with a feed-forward neural network, which is what this is. There's a feed-forward neural network. So so the average, so that averaging, what does averaging give us? What is it, like, what does it capture?
I feel like averaging would actually like be somewhat troublesome if you had, 10 different vectors from one user and 10 different vectors from a different user. And they were all different vectors, but theoretically they could have the same average. Is that not a big problem that arises, or a common problem that arises, or?
So yeah, that could be a problem, especially if there are two users, where one of them has changed his preferences recently and the other one has had these preferences before, so they are actually kind of switched. So someone likes sports videos now, but they used to like music videos before, and the other person likes music videos now, but they used to like sports videos before. So they've kind of swapped their interests. But the average, without any weightage or without any importance to the time, is going to give them the same vector, which is incorrect. And even for any of these users, maybe you want to highlight sports more because it's more recent. So those kind of issues would come up. But otherwise, if two users have a really wide variety of interests and you kind of account for timing and then they're the same, then the averaging is telling you, well, you know what, they kind of like these 5 different categories of videos. So that wouldn't be so bad. So once you account for biases, average is not such a bad baseline for an understanding. But obviously the timing is going to come up as a factor. The frequency is going to come up. Maybe I watched 3 seasons. I binge watched 3 seasons of a particular genre of, maybe I watch comedy, and then there's a comedy show. Someone said it's popular, so I watched like 30 videos of comedy, and that counted as 30, whereas they were all like part of the same series or the same show. But then I watched like 10 other videos in sports in different channels, So that will bias me towards comedy, which I was just binge watching once.
Yeah.
So those would have to be accounted for when averaging. Otherwise, they're going to bias the results, right?
Yeah, I suppose those factors could be added in as like weighted embedded factors. So that would actually probably take care of most of that averaging problem. That's a good point.
Yeah. So weighted average is probably better. Yeah, that's a good one. So yeah, so they use embedded video watches. They also use embedded search tokens. So again, this is basically capturing the user profile, right? So what has the user done? Well, they've watched videos completely. Let's take all those videos, average them. What else have they done? They've also searched for, they've had search tokens. So they've searched for, I don't know, I want to watch a comedy show by Russell Peters. Okay, so I've searched for that. So then what this is doing is it's learning embeddings for the tokens and then getting those embeddings and averaging them across all the search history of the user. And that could be defined over a time period. But so this is capturing the search component of the user. And this is also important because if you think about it, I might search for something and I get 10 results, but I only watch one. So the watch is going to capture the specific things that you watched. The search is telling you, hey, if you actually watch something else, that was not captured in the video watch, but it's captured in the search because it's more broader. It gives you a higher level understanding of what the user is thinking of or thinking about. And that's put in here as a search vector. So you kind of, this is a concatenation of different signals. So watch vector, search vector. This could be other things like where the user's embedded. Like I'm in the States, or I'm in India, or I'm in China. That could impact my viewing patterns as well. Like even if I live in the States and I go to China, my viewing might change because I have some local influence coming in. So where I'm located might have an impact on me, even if I know what I like to watch, right? So they were sharing in this paper that even though they're using neural network and everything, it was important to capture these different streams of data and different signals to get better recommendations. And I think freshness was a very important thing, like making sure the recommendations are capturing recent uploads to YouTube by different content providers was important. So that's, I think the way they did it is they didn't randomly pick a subset of what the user has watched as the target for this model. So you hold back, like you have some videos from the past that you use for like pass in as input, and the output is what you would like the model to predict as something that they would be interested in watching. But instead of having a random subset of what you watched as the output, have the most recent videos that the user watched as the output. So you're using like the past to predict the near future, which is a good one because that's going to bias towards predicting more recent videos, right? Or more recent watches of the user, which might also be more recent video uploads to YouTube, or capture some freshness. So the freshness can be explicitly modeled, but also if you choose your training data in this way, it will also bias more towards the freshness as well. There's also gender, age, and stuff. And then, so once you have all this is a wide layer of embeddings concatenated. Then you have some sequence of like maybe 3-layer, 4-layer neural network. And then in training, you're doing a softmax, which makes sense to predict class probabilities. So across these million videos, so you have million classes, and you're predicting probabilities across these million videos, and then maybe pick the top 1,000 of those probabilities, like the top 1,000 probabilities, highest probabilities, and then say that's my filtering after the candidate generation stage, or 100, right? So here we're looking at 100, and then those 100 go to ranking the next model. And then there's also serving or inference stage. So I've trained the model, and I've already done training. So now at inference time, what I'm going to do is I get, so basically the softmax here at this stage, you also get the video embeddings, because whichever, so if you look at the output, so let's say this refers to video 100. So these weights that go out from this particular output layer to the layer before is going to be a natural video embedding, right? Because that's telling you, that's going to be a dot product with the features before and the layer before. And the layer before is all the user. There's no video that's showing up. The video only shows up in the output layer, the video that you want to predict. So that naturally means you're doing a kind of a dot product and then doing some nonlinear function around it. So that means these weights that go from the last but one layer to the last layer for every single video slot is giving you the embedding for the video. So that's what this is saying, is that the video embedding comes from the last but one layer. And then for any user, and you kind of like do the nearest neighbor search, and then you get the top end. Right. Okay. All right. So even if you've trained, you've trained the user before, but then everything keeps changing, watch history keeps changing. So every time you see a user, their profile has changed. So at that point, the user vector gets computed once. The video vectors are probably already computed from before, so you don't have to worry about it. Now it's just a matter of getting the user vector, and once you get the user vector, just do nearest neighbor search by taking using a nearest neighbor search algorithm with some cosine similarity or Euclidean distance or something, dot products, and get the top end results. So every time a user comes to YouTube, you would do a nearest neighbor search. And assuming, so if you already updated the user's vector, then you don't have to go through these neural network layers at inference time. You already know, oh, you can cache it. So you can say, oh, this user, oh, actually, you know what? I've already computed their user vector. So I have it in memory. Now I just need to do approximate nearest neighbor search. So that I would have to do, and that can be very efficient. So that can give me maybe less than 100 millisecond latency. But if I've not updated the user vector, I'd have to go through these layers and get the user vector. Video vectors are already there. And now I'll do approximate nearest neighbor search. So that's going to be an extra step. Any questions on the architecture of the candidate generation stage? And it's not enough to generate the top 100 videos once a user shows up, because that's just candidate generation. You have to pass it through the ranking model as well, which is coming up. So the latency is the sum of the candidate generation stage and the ranking stage as well. So that's the total latency that adds up. Okay, let's do an in-class exercise. So take a look at this question. Maybe take a minute or two. And just look at this and then answer the question. Okay, what's your answer?
I said A because it was video content of the user and not necessarily a combination of users.
Yeah, let's look at the model, right? So there is definitely the video content, um, but also this video content corresponds to what the user has watched. So that's collaborative filtering, right? Collab-
Yeah, I couldn't remember the exact definition of collaborative. I thought it was the recommendation is based off of user similarity, but if it's using behavioral data of the user, then the hybrid model would make more sense.
So actually, yeah. So I think we can clarify the terminology here. The collaborative filtering actually represents to user interaction with products or items, or
Oh, okay,
so just that interaction, just that matrix where
gotcha.
without any content, you don't have any extra information on the videos or the items or the user themselves, except that they interacted with this item or this video. So that's collaborative filtering. Content-based filtering is you actually use features for users, features for the content, and then make recommendations. So basically you say the user watched this video, and then I use the content of the video to understand other videos that are similar to this video, and that is being used to make a recommendation. And hybrid is when you actually have both. So you have behavior, which is interaction between the user and the content and the items, but also you have features based on the content of the items themselves. So here we have both, right? Because you have user behavior, like which videos did they watch? That's user behavior data. But also we're using content for the uh, the videos themselves, right? Does that make sense?
Yes, yes, it does.
Let's do one more in-class exercise. Okay. Any thoughts on this?
I'm not entirely sure what ranking loss is.
Yeah, I don't think we've covered it yet. Yeah. So, right. So it's not ranking loss.
Right, that's what I was going to assume because we hadn't gone over it. I would say probably. Um, Wait, you said it was a softmax.
Yeah. So softmax cross entropy loss, right?
Yeah.
So it's basically, looking at the probability of the predicted probability versus the true probability, and the loss between the two is cross entropy loss. So that usually gets softmax is what we use to get the predicted probability, and cross entropy is measuring the distance between the predicted probability and the true probability, which is basically um, connected to the videos that were left out or which are watched by the user, um, or which we want to predict, right? So it's cross entropy loss. Okay. And it's multi-class classification. So typically multi-class classification is cross entropy loss.
Would this be a scenario where sparse cross entropy loss would be useful? Because there's like, a million videos in your, or because it's a probability that sums to one, it wouldn't be useful because you just take the top, 100 or 1,000 or whatever.
Yeah, sparse cross entropy loss it makes sense. I mean, in practice, when you compute the cross entropy loss, we know that even if the predicted probability is non-zero across all the million videos, the true probability is actually going to be non-zero only for the videos watched by the user in the recent past, right? In the recent.
Right.
So that's going to be like maybe 100. I don't know, not more than 100, right?
Yeah.
Or so. So the rest is zero. Because the rest is zero, that's not going to matter. So you don't have to worry about the rest. Just focus on those 100. So when you actually compute the cross entropy loss, it's very efficient. Just focus on
It's only for the 100. Okay.
what's non-zero there. Yeah. And
Okay, that makes sense.
look at the probability that's corresponding to those 100 and see if those are high, then your cross entropy loss is low. If that's low, then it's high, right? Yeah. So the YouTube paper had experiments on depth. So as you increase the depth, how does this is mean average precision. How does the precision change? And they had different categories as well. So they had like using only watches of the user, using watches and searches, using watches, searches, and some other information and all features. So obviously there is a bump. So this is the value of search. There is a bump between just using the watch history of the user versus actually using search history as well. What have they searched in the past? So this is a bump in the precision, which is doesn't seem much, but it's actually pretty significant. 2% is a lot. I mean, it can translate to $1 million revenue or whatever, so equivalent. And then there's a small bump when you add some other features, and then you use all the features. You see this, and this is showing how the precision improves with depth. So there is probably an improvement from going from 0 to 1, which means use nonlinear, some kind of nonlinearity in the model. And there's also probably a slight bump from 1 to 2, but nothing much after this. So 2 layers and more, I don't see. Maybe using all the features, there's a little bit of a bump. So adding more layers is not helpful beyond a certain point, is what was observation here. So do you add 1, 2, 3, 4 Rayleigh layers? Maybe add 2 because it's kind of tapering off. And if you don't have much improvement in precision, adding more layers means more inference time. So you want to save on inference time. So just have the minimum required to get a good precision. And this is a ranking model. So this is the second stage of the YouTube model. And this, as you can see, looks pretty sophisticated. And it has a lot of information. And if you notice, it's actually the input it's pairing a user plus a video. So here at this stage, we want to rank, let's say 100 videos, right? So I want to see for this user, for this video, what's the match? What's the score? So just pair them, just pair a user with all the videos. So that's going to give you 100 different inputs, and then pass those inputs, and then you get, you have a logistic regression model. So that's going to give you a logistic loss function. So that's going to give you a score, 0 or 1, or something in between 0 and 1. So that's going to give you a probability, and then take all these probabilities and then sort them, and that's going to be your ranking, right? So that's why this, in the previous candidate generation model, we're looking at a specific user and then trying to predict their videos. the videos that they would watch in the future. Here, we're pairing a user with a video and looking at how good is that pairing. You see the difference? So here, what's happening is you have, let's say you have video, let's say this is the candidate video. And this is user watch history. So I'm going to use green for video features, and then maybe red for user features. So you can see this is a user feature. This is both a user and a video feature. It's a video feature, and a video feature. So you see the green ticks. The green ticks are video features, and the red ticks are user features. Right. Time since last watch. Yeah, so this is also user feature. So user video feature. So we have exclusive user features, exclusive video features, and a combination. So for example, here, time since last watch, you're looking at time since last watch of this user for this particular video, right? So if it's been a long time, maybe they want to watch it again and you can recommend it. So that's, and then number of previous impressions. How many times have you showed this video before as a recommendation and they've ignored it? The more number of times you've shown them and they've ignored it, maybe they don't want to watch it, so don't recommend it, right? So that's a user video interaction feature. User language, what language do they usually watch it? So that's, and then what language is the video in? So if those don't match as much, then maybe don't recommend the video. And then there is some averaging, and this is like a wide layer. So wide layer with concatenation. And then pass it through some ReLU activation functions and hidden layers, and then train and then serve, right? So here you can see it's a logistic, because just take a linear combination of the weights from the last layer and then exponentiate it, and that gives you a probability between 0 and 1. So if it's 1, that means you must definitely recommend the video to the user. If it's close to 0, then don't recommend. And if it's something in between, then rank and then figure out. So the probabilities are just going to be used for ranking, and then good. So in practice, when you train, you're going to use a logistic model for probability, and then embed it into a loss function. But when you serve, you don't need to exponentiate and do all of that. Just compute this, and that's going to be proportional to the ranking, right? So just compute that and then look at the score and then rank it, and then you're done. Just sort it and you're done. Any questions on the ranking model? Questions or thoughts?
This is one video comparison at a time, right? Or is this all 100 put into a matrix and fed through?
Yeah. So this is, that's a good question. So this is one video plus one user features.
Okay.
So
then you have to like cache these, do all of them, and then like sort based on the ending probability.
Yeah. So the good news is you only have to do it 100 times. Because you're looking at so I have a user, like you showed up online and you're on YouTube and you refresh. By the time you refresh, all of this should have happened and you get a new set of videos, right? In that refresh time, you've already done candidate generation. Now for you, so I'm the user, I have 100 candidates that have come up from the candidate generation stage. I'm going to pass in my features, the videos features, the joint features for every single video. So that's 100 times. Pass it through this network. And then, so probably what they would do on YouTube or something is they would just have multiple servers in which
It's
you can
running parallel.
just send in the user ID, send in the video ID, and then let it figure out all the features, and then in parallel generate all the scores, and then pass it back and rank. So I mean, I don't have the exact details, but I think that's my best guess there.
Thank you.
So how else would you do it? Because the candidates are not in my hand, right? The candidates are going to be coming from upstream. So I cannot predict, like I cannot fix the 100 candidate videos as my output, because those candidates can keep changing. Does that make sense?
I mean, because it's dynamic, you have to do real-time inference on it, right?
Yeah, and you have to make user video comparison in a
Right.
model. A model has to have a user input and a video input, and then it compares and it generates a score. Like you cannot just generate scores for all the videos, because we don't know. How do you tell the model, well, these are the videos you need to score at once in a neural network setting? How do you fix the output layer to be those exact 100 videos? We can't, right? And this is normal in ranking. You just have user video interactions. So you just kind of search across all these other videos, and then basically you're taking dot products between this user and this video, but in a very sophisticated way by passing it through this neural network model.
Right.
And yeah, you have to do this as like you have to pass through all of this in inference. You cannot cache it, because these combinations can be very, very unique. You've never seen them before. So that, but if you can do, if you can do any one of this combination in like very low latency, and you don't have many such combinations, then you can parallelize it or do it quickly. And that's why we need to limit the number of candidates that we are ranking through this model, because we're not able to cache certain things.
I imagine the smaller amount of candidates that you have, the better off you are. So if you generated more candidates, or if you generated more refined candidates, you could have this lower latency model. So that means you'd have to have a more complex model as candidate generation. Would that be right?
Yeah. And then if you have some parallel inference framework, then you can go up to the limit of that framework. So without doubling or tripling the time, because you're waiting for the results to come out before sending the next batch. So if your batch size of the candidates is equal to the number of parallel servers on which you're running this inference, that would be a good match.
Yeah.
But it's very interesting, because before you could have cached the user, and you could have just skipped all of this and gone right into the approximate KNN. But here you're not able to do that. And that's why you have to limit. It's a sophisticated model where everything's like meshed up, but you do it for a few candidates. And it can be very accurate. Yeah, because there's a lot of pairwise interactions happening here. So that's going to make it more accurate. And because you've already done candidate generation, you already know the candidates are good for the user. So the model is going to pick on the fine differences between these videos because these videos are already good for the user. So that's going to really help with the ranking part. Okay, so we highly recommend taking a look at the reference here. This is a YouTube paper from 2016, has more details on the model as well. I just want to run through a couple of other examples in other companies, and then we'll wrap up for today. So Alibaba is also uses something similar. They have a matching module, kind of like you can say candidate generation and filtering. That says these are kind of good, but they're not necessarily ranked, and then they actually rank. So you take all these, let's say you generate 500 items, you take these 500 items and then rank them from 1 to 500. That gives you a different order. Pinterest is dealing with billions of pins. So instead of a million videos, we're looking at billion pins. And then they have a funnel that kind of goes from these billion pills and does some kind of heuristic sorting and generates thousands of candidates. And then they have a full ranking model, which is similar to what we saw on YouTube, that will take these 1,000 and rank them in a good fashion and then generate hundreds of pins. And those would be the recommended pins. So I searched for recommendations ranking on LinkedIn again, and I came across certain job profiles. So let's look at some keywords here. Push the boundaries of real-world ranking, recommendation, and optimization systems. Support science engineering. Okay, this is all generic stuff. Recommendation services team, scalable machine learning solutions to personalize and optimize customer experience. Okay, AI for recommendation systems. Okay. So yeah, slightly different from search ranking. Actually quite different, can be quite different. But the search, so these days, whenever you have the context of machine learning, search ranking and recommendation ranking kind of overlap a lot. So you can use search ranking methods for the final ranking stage. Like we spoke about ranking loss, we'll cover it in the next lecture. So ranking loss, ranking metrics, learning to rank, all these are borrowed from the ranking literature, but for recommendations. So, but typically these days, the context of using machine learning for ranking is mostly in recommendations. There's also a little bit of search ranking. I think search ranking also, yeah. So the difference between search ranking and recommendation ranking is in search ranking, you're searching and then you're ranking. So you can still have search and rank in a retail page, I guess. Yeah, but I suspect a lot of models will be similar in between the two. Here's an example we spoke about earlier. So this is Instagram. They're looking at billions again, billions of items, and then filter it down to 500 candidates, and then have 25 as your final list that you would recommend as images or videos or that you would want the user to watch. I think especially for Reels, it's very important that you get the Reels right to keep the customer engaged. And I think with Reels, the next Reel prediction is very important and has to use what I'm watching right now. Maybe I'm looking at comedy in Reels, and then I don't want you to show me a documentary right after. So maybe I'm biased towards what I'm watching right now. I want to see more comedy. I'm in the flow of watching this. Does that ring a bell, or do you guys see that behavior?
I think with Instagram in particular, I don't have TikTok, but I heard that their algorithm is like pretty pretty cool with that, in doing like very good recommendations based on the stuff that you're watching right now. I do use Instagram, and I do have a lot of like really similar recommendations. And then all of a sudden it'll like, jump to like something, a different category. But to be honest, that's almost what I want as a user. Like, I don't want to be sitting there scrolling through dogs for a half an hour. I want to be sitting there scrolling through dogs and cats. Like
Yeah,
I want that variability in it. And
yeah.
so I think it actually does a pretty dang good job, at least for me as a user.
No, no, I think Insta Reels are, I think it's pretty good. And I think YouTube has come up with shorts, YouTube shorts, and then TikTok is anyway there. But I think here there is this element of session recommendations. So you're in a session and maybe you're in a flow and you want to keep watching something similar. But then you have a variety of interests. So if you get into a different session and your mood is changed, maybe you want a different variety, but then again, you want to navigate in that space. So that could be one way of thinking about it, but it's interesting. Or maybe if you build a recommender, you would test out the mood of the user and say, what are you really interested? You like music, you like comedy, but are you into music right now or into comedy? Let me see. Let me show you a few musical pieces and some comedy, and then let's see which ones you're skipping and which ones you're actually watching. So as the session's going on, maybe I already learn a local model of what you like and then bias the generic model towards that. So interesting. There's like a lot of interesting things you can be done.
Pretty complex. The amount of real time.
I know, especially real time, right? Yeah. I think we spoke about this, the candidate generation Instagram. This is from, again, you can look at Instagram recommendations. This is a reference for it. Um, so how do they generate candidates? Well, you liked a photo that Alice posted, which is similar to Bob, who posted these photos, and so these become my candidates. And then Alice is similar to some other user, or maybe the photo is similar to other photos, so those also generate candidates. So you can just do candidate expansion and generate a bunch of candidates. uh, Video ranking, yeah, so I think this is there's a paper here where they don't give a lot of details, but um, using past streaming behavior to learn patterns and predict videos popularity using ensembles. So um, again, they basically looking at engaging customers in on Amazon Video and looking at what streams of data. So this is about what streams of data would be useful for ranking. Uh, but it's more. This one's more of I think this is more of a recommendation model than a two-stage model. So this one was a little bit different. Um, yeah. So some of the references for today's lecture. Feel free to take a look. I highly recommend this one, and also Pinterest. Um, and also Instagram. Yeah, these are more very comprehensive. Next class we'll go into what's ranking loss. So we're going to go into search ranking. We're looking at recommendations ranking. We're going to go into search ranking, ranking loss functions, learning to rank, which is like a classical, like learning to rank is like how do you learn a rank? Like how do you learn to predict multiple classes? That's multi-class classification. How do you learn to rank is learning to rank. And then what are some challenges in search ranking, and what are some metrics in ranking that are used to measure goodness of a rank? And these are different from recommendation metrics. So recommendation metrics are precision, recall, F1 score. But if you're also doing ranking in recommendations, now you have recommendation metrics, you have ranking metrics, because you're also doing ranking. So you have ranking metrics as well. And then you have online metrics, which is A/B testing. So you have like a lot of metrics to use for your problem. Okay. Any thoughts or questions It's fine. Okay, then, so we'll see you guys on Wednesday and we'll do search ranking. And machine learning. So again, search ranking as traditional, this is like traditional approaches. And then there's ML based, because you can do search ranking in many ways, don't need to use machine learning, but we'll focus on machine learning approaches to search ranking, which has been more recent. So they call it neural approaches to ranking, basically using neural networks. Because the traditional one is like, if you look at information retrieval literature, they have a lot of different heuristics for search ranking. But more recently, the machine learning has kind of filtered into search ranking as well, and so that's what we'll focus on next lecture. Okay, sounds good. See you guys on Wednesday.